Okay, so we stopped here in implementation of Mandelbrot set in Python. And the code looks quite similar to C++ and Fortran, but you can also notice that it's a bit shorter. So the entire calling the subroutine and writing the subroutine is only one page. So clearly this, in some sense, it's improvement. So let me start with the innermost loop. Innermost loop here is a for loop. For is like do loop in Fortran. In some sense, it's similar than in C++. In C++, we would say for ETR is equal to 0, ETR is less than max steps, plus ETR, isn't it? But in Fortran, in Python, we just use this so-called range function. We're going to talk about this much more, but range basically just means this creates an array 0, 1, 2, up to max steps minus 1. Okay, so and we are iterating, ITR goes over all these numbers. We're going to discuss more about this later on, but for now we just can think of it as the simplest possible for loop. Okay, and then what do we do inside this for loop? Just like in all other languages, we always do calculate z squared plus z naught, and we assign the z squared plus z naught into z, isn't it? This is our new z. And then we check inside the loop if absolute value of z is bigger than 2, then we have to jump out. So this means jump out. The function is done. Now the slightly different, slightly new thing in Fortran, in Python, is that the complex number is initialized with this J symbol. So whenever you write a floating point number and then append J to it, it means it's a complex number. So for example, 1J would be a complex number, or 3J would be a complex number, isn't it? And 3J actually, mathematically, this is equivalent to 3 times I, isn't it? So J is basically like imaginary unit. And you should not write 3 times J. Okay, 3 times J, it's would mean something else. Then if you write in Fortran, in Python 3 times J, it would mean 3 times J, where J is the variable. Okay, J itself is meant to be a variable, isn't it? But if you don't write times, if you just write floating point number immediately followed by J, this means a complex number. Okay, it's just a syntax for in Python. And 0J then, of course, means a complex number that is 0. The real and imaginary component is 0. Actually, in this case, probably things would work even if we set z is equal to 0 and we don't write the complex number in front, because Python is a so-called automatic auto type, which means that in this statement here, down here, z would immediately convert to complex number if it was a real number at the beginning. So let's say the z was a real number at the beginning. Then in this statement where we add z naught, and z naught is a complex number, for example, the code will understand that it needs to create z to be a complex number, and it will probably work. I'm not 100% sure, but I think it should work. So it's of course much safer to start with the correct type and at the very top, and use the correct type all the way through, isn't it? But in general, it turns out that as long as there is a simple conversion between different types, Python will try to convert properly the types during execution. Okay. Yeah. So now we discussed this part of this function, which is basically algorithm is exactly identical to what we wrote in Fortran and C before. And then how do we use it? Well, we call this function here. isn't it? Where we when we start our Z naught, isn't it? The input is Z naught, which is basically this two-dimensional grid which we want to display. So this grid, of course, goes from minimum x to maximum x, and from minimum y to maximum y. So x goes from minimum x to maximum x, and y goes from minimum y to maximum y. And y has to become purely imaginary, isn't it? Therefore, we multiply y with 1j, which is the imaginary unit. So 1j is the imaginary unit, isn't it? Because it's 1 times imaginary unit. And the second argument is max steps. Now we use max steps to be 1,000, and the grid, the array grid for our plot is going to be 1,000 by 1,000. And so then, well, we have this two do loops for I and for j in x and y direction. Now this statement here allocates a two-dimensional array. So this is so-called allocation of a two-dimensional array. So the important point is that it's very, very easy to allocate two-dimensional arrays, numpy arrays. So basically this is a numpy array. And all we need to specify is the x and y dimension of the array. And since there are two numbers here, it means it's two-dimensional array. We can use this construction zeros. We could also use ones of nx and ny, for example, and ones will initialize the entire array that every component has a unity in it. So 1, 1, 1, 1, 1, 1, isn't it, for the two-dimensional array? Zeros means that everything is set to 0. Of course, this is most commonly what we need is basically zeroing the entire array. So this statement here, zeros, means that it does two things. It allocates the array and at the same time zeros it. Okay, that's two things. Of course, the nice thing in Python is that deallocation of the arrays is going to be automatically done. User should never see any deallocation or anything like that. So of course, everything is done automatically. Okay, so now once we have this array, we just fill it in. So into I and j component, isn't it? So I, j is properly each pixel that we're going to display is saved here. And the reason that we do this is because we want to separate computation time for computation from time for displaying results. And therefore, we are going to, after the computation is done, we are going to print the time. And so we look at the time at the beginning, we look at the time at the end, and we write how much time has been spent in calculation only. And after this timing is done, then we display the result with so-called imshow. Now, what is the imshow? I think I have a question. Why if name has? Okay. So there was somebody in the chat, Shan Ren, asked me, why is this if name is equal to main? And I will come to that just in a second. But let me first explain this imshow. So now we are using something which is called pylab. So we import here from pylab import star. This pylab is basically the plotting library inside Python. We're going to go into details of this later on, but it's really very capable plotting environment or plotting library. And one of the functions inside this library is imshow. And imshow is basically just displaying pixel by pixel floating point numbers. Okay, if you have a two-dimensional array of floating point numbers, you do imshow on them, and you will have basically a two-dimensional density plot. Okay. Now we are gonna. It turns out that this ImShow always plots data from in y direction first. So basically, the data is displayed in this direction. Okay. So it starts at the very top, and then it goes down in y direction, and then next in y direction, and so on, and then yeah. So however, the way we save the data here is in such a way that the first component is x direction. So in order to display it properly, we need to transpose the array. Do you understand that? So of course, if we switch these to I and j here, then we could immediately display with ImShow. We wouldn't need this transpose, of course.
Question.
Yeah.
So in the double loop, we use the j.
Yes.
And there's also a complex j. So
Yes.
how does the system like?
They don't interfere. They don't interfere. That's a good question. Yes. J as a variable. If you have a j here as a variable, it's completely has completely no interference with one j. Okay. Why? Because as I said before, if you have a floating point number immediately following j, that means a complex number. Has nothing to do with the variable j. It has to immediately follow floating point number. Okay.
I see.
Yeah.
Thank you.
Why do you have that 1 over data inside the transpose?
Okay. That's a good question.
In ImShow.
Yes. I could also plot just the data. Okay. The plot would be different, would look different. Okay. Why 1 over data? Because you remember those the points which remain in the Mandelbrot set will appear in data as a very, very large number, maximum steps, isn't it? So whatever is in the Mandelbrot set, it will give you 1,000. And whatever is not in the Mandelbrot set is going to be something that is smaller than 1,000, isn't it? And then if you do 1 over that, it means that things that are in the Mandelbrot set are very close to 0, and things that are not in Mandelbrot set are closer to 1. Okay, and it turns out that when you plot something that, as a density, it's easier to visualize when number goes between 0 to 1 than when number goes between 1 and 1,000. I mean, it's just a way of color coding things. Okay, but later on we were going to also display just data, and then you will see slightly different. I mean, image has the same information, but of course colors look different. So it's just a way of displaying data. But transpose is important, because if you don't transpose, then you see the Mandelbrot set turn on its head, isn't it? X and Y are changed. What else? Yeah, so basically we can also, I mean, there is also a way of displaying things in this direction, for example, starting from below and going up. In this case, you need to change. You need to add an option into transpose. Into ImShow. So if we add here into ImShow something which is called origin, you can say origin is top or bottom. I think. I mean, we could specify. I think it's top or bottom. If we do that, then basically you flip around the top from the bottom. You flip them around, if you want to, of course. Okay, yeah, and whenever we use Python plotting utility, you need to use something which is called show in the end. So because you can throw lots of different plots on this display, and once you have all the plots thrown on the display, at the end you write show, and that actually produces the plot and displays it. Okay, so this show actually produces the plot in this place. Well, before we were just throwing things into the display in some sense, but things were not really plotted yet. Okay. Yeah, and this is, of course, this type of plotting is faster than writing to the disk and then displaying things from the disk. So you will see that it's much more efficient, just keeping everything in memory and displaying it instantly. Now, finally, I can return back to the question, why do we use this if name is equal to main that Shang asked me. In this particular case, we would not need that. So for example, I could just remove this thing and then I would need to justify the entire text following this back for this back to the beginning, isn't it? And this would work. But why did I do that? Well, it's always a good idea to use this if name is equal to main, because this says the following. Imagine that I'm building a library rather than having an executable. So let's say that this manp.py that I want to later on use it as a library. If I use it as a library, as a Python module, then Python module will have only this subroutine here, or basically this function defined, while anything that comes below this name is equal to main is basically just testing Python module. Okay, so normally whatever it comes here below if name is equal to main is meant to be testing the existing set of functions inside module. Okay, and every Python file, in some sense, is a Python module. That's the philosophy of Python. Every Python file is actually a Python module, and module can contain data, variables. It can contain functions, and it can contain a code which tests the functions. And the code which tests the functions in this case appear below if name is equal to main. Okay, what actually this thing does is very simple. It turns out that if you invoke this, let me go to compare languages. Yeah, if I do this manp.py, if I invoke it like this, Python manp.py, in this case, name, the construction name will be main. Okay, name underscore name variable will have a content which is equal to main, and therefore things will get executed. However, if I decide that I'm not going to call manp.py in this way, but I'm going to create some other module like xxx.py, and then I'm going to do import manp, okay? And this import manp here is completely legitimate. What I'm doing is I'm just using the same file or the same Python module in slightly different way, importing it into some other module, okay? In this case, it turns out that this underscore name will be called xxxx, okay? Because actually the content from which I'm calling this module is not shell, okay? But it's some other routine, okay? And in this case, it turns out that this name is going to be different. In this case, it's going to be the name of this file, okay? And therefore, this everything that is below this if statement, so anything that follows the if statement, will not be executed, will be ignored. Okay. Again, this is useful when you this is useful because we many times put the code that tests the functions below the statement. Okay, is it clear? Sean, is it clear? Sean, did you disappear?
Well, actually, it's not very convenient for me to talk. So, because my roommate also has a video video meeting. So I prefer to type in the chat channel.
Okay.
Yeah. Yeah. Thank you so much. It's very clear to me now. Yeah.
Okay. Okay.
Yeah.
Yeah. So let's go. So we discussed this implementation. Hopefully, we understand it now. Now, how do you test all these examples? Fortran code we already executed, and C code we already executed. What we are using here is this symbol greater. The symbol greater basically means that anything that's being printed, it should be printed in the standard output, is being redirected. This is redirection to the file. So we are redirecting all the output to the file, which is mandi.dat. Okay, and then later on we can use this to plot things with nuplot, which we already done before. Now in Python, of course, we don't need to redirect anything. We're going to directly use Python with just executing the code. Okay. Now hopefully you've done this yourself, and if you didn't, you can still try to improve your environment so that you're going to be able to test all these functions. On my computer, yeah, I'm executing here Python. It takes 25 seconds or something like this to get Python code executed. Almost done, hopefully. Coming a little bit more. Well, whenever I run Zoom, it's slower. Okay, 31. So when I run Zoom, it turns out that this is a bit slower, but it finally got displayed. Yeah, so the timing on my computer are the following. So C code has a clock time on 1.3 seconds, but actually the real world time is only 0.2 seconds. Now, as we discussed before, the difference here is because I'm using OpenMP. So because I'm using multi-core execution on many cores, or on 8 cores that I have here, I can get the execution time down to 0.2 seconds. So it's really fast. Now, similar Fortran is also the order of 0.2 seconds and clock time 1.2 seconds. So one would say that Fortran and C are more or less of the same order of same speed. Now, Perl is incredibly slow. It's more than 5,000 times slower than compilers, just completely useless for our purposes. And Python is 25 times slower than one core. And if you compare this to the timing on multi-core, then it's 5 times 25. So it's still 100 times slower or something. So yeah, I mean, Python is not terribly fast, but it's not terribly slow either. But the important point is that both interpreters are substantially slower than compilers. Python is substantially faster than Perl, as we clearly see. And C++ and Fortran timings are similar, of course, much faster than interpreters. Yeah, homework we already discussed last time, so get familiarity with those installations. And now the subject we want to discuss here is how to improve the Python performance. I mean, we are going to base our class mostly on Python, and therefore we need to know how to make Python substantially faster than this roughly 1 order of magnitude slower than C and Fortran. It's not good enough. 1 order or 2 orders of magnitude slower than Fortran or C. It's not good enough for most purposes in scientific computing. We want to have it faster. So what can we do? Okay, so I wrote here down 4, maybe 5 strategies of how to improve that performance. So the most simple strategy is to find routines which are already in library and properly implemented. Why? Because these libraries, NumPy and SciPy libraries, already contain a lot of standard algorithms that we might need. And if you can translate your problem into one of the standard algorithms, so they can use one of the standard algorithms, then all you need to do is to learn how to call this standard function or standard algorithm from SciPy or NumPy. We're going to go in details through those through some of those libraries so that you get a feeling of how the libraries look like. But this is always a good idea to have in mind. So if you're doing some linear algebra, then pretty much any linear algebra is inside SciPy, even inside NumPy now. If you do any, let's say, root finding, then root finding is already available in SciPy. If you're doing some minimization, minimization is definitely available in SciPy. If you do integration, it's also available. One-dimensional, two-dimensional, even three-dimensional integration is available in SciPy. What else? Solving a system of differential equations, that's already available in SciPy. It's hard to beat it, okay? Pretty much any numerical thing that you would, if you open the standard book on numerical recipes and you go through numerical recipes, basically I can guarantee you that more than 90% of numerical recipes book is already implemented in SciPy, okay? So therefore, in any such instance, the only thing that you need to do is you need to learn how to call the routines from SciPy. And these are extremely optimized because they're actually all written in either Fortran or C++. You're just calling the Fortran code, and therefore it's as fast as it could be. Okay, so that's the first strategy, and it's a very important strategy. But nevertheless, sometimes we need to write different algorithms that exist, or you cannot translate it into one of the standard algorithms that might be already implemented, and we need to have some do loops. And in this case, you can use the following strategies. We could use so-called numba. Now, if you're interested, you can look at the webpage here, numbapydata.org. The nice thing about numba is that it requires almost no work from the user. Okay, we will see basically that it's just adding 2 lines in your code, and if numba works, that's all there is to it. Just adding 2 lines in the entire code, and it's just a Python code. Now, the drawback is that a user has, well, we have very little control of what numba does in the background. It's all kind of semi-automatic. It's a bit of a mystery, or yeah, it's mysterious. Okay, basically, what numba is supposed to do is it looks at your Python code, which is supposed to be written in kind of a simple way for numba to as simple as possible for numba to translate to C++. So you can think of it as writing almost a C++ code, okay? And then so that numba will have easy time to translate it into C++ code behind, so you don't see that, but you can expect that there is a C++ code somewhere that you don't see in some temporary directory. And basically next time you, well, when you execute this thing, actually the C++ code is being executed, not the Python code, okay? So behind your back, without you knowing, actually it turns out that there is a C++ code somewhere, okay? That's what this numba is supposed to do. Yeah, so this helps when there are slow for loops. So you have many for loops, and for loops in Python are incredibly slow. If they're similar, if you have many repeated operations in certain code, and of course for loops are a typical way of making repeated operations. And one thing that I learned, and it's also explained in the webpage, is that one needs to experiment with this numba a little bit. So one could rewrite your code, your Python code, a little bit in several different ways to understand and basically use this different codes with numba and see which one is faster. Because it turns out that some codes tend to be slower in Python. So you rewrite the code, and the Python code, the new Python code, is slower. But it turns out that when you switch on numba, it's faster, okay? So in some sense, the way I think of it is that if you try to write your code in such a way that it looks more or less what you would write in C++, then numba tend to be more efficient. Okay. Of course, that's easier said than done. I mean, I also don't know exactly what to do in order to make it fast, but the best thing is to experiment, invoke this add the simple numba statement and see if it helps. It's fine. If it doesn't help, well, then we need to do something else. Okay. Then this next way is to recode the slow loop in Fortran and then use f2pi. Now, the good thing about this using f2pi is that you are guaranteed to get the performance of Fortran. Okay, so here there is no mystery in the back. There is nothing like mysterious automatic conversion of for loops into some C++ code, but you are in control. You as a coder are in control of the code, and you are guaranteed to actually get the maximum performance. The drawback is that you need to do it by hand. So you need to create a Fortran code, and you need to use this f2pi to change the Fortran code into Python module, and then you can invoke the Python module. We will do this, and we will show how this is done. In similar way, you can use pybint11 to do similar things with C++. So you can rewrite your innermost loop with C++. You can use pybint11 to create Python module, and then you can use this in CyPython. Now, the important point here is that you can combine any number of those different ways inside Python. So I can decide, for example, that most of my code is just fine in Python. It can be written in Python because it's not the critical part of the code, which takes most of the time. And then I see that the small part of the code actually takes almost all the time, and that's what I need to speed up. There is so-called 80-20 rules, which usually means 20% or less of the code takes 80% of the time, and that's the code I want to concentrate on. And then I can decide that part of this code is actually very easy to write in Fortran, and I'm going to use a little Fortran routine. I'm going to add f2pi on it, and I'm going to have this part of the code written in Fortran. And then I decide for a slightly different part of the code, maybe C++ is easier. I write some little snippet in C++. I use pybint11 and also take this into Python and then glue everything together. So Python is kind of a glue that can put together all kinds of codes, a little bit of C++, a little bit of Fortran, and maybe even a little bit of Python with numba. All this can be used in the same Python module. That's the beauty of this. Okay, so you can think of Python as a glue for different types of codes. Okay. Now the fifth strategy, unfortunately, it was weave, and I really love this weave because you could write almost like we used to. Well, we could write in exactly the same way that we used to write assembler code inside C. You could write like an little inline code and just sneak it into Python code, and it would get executed and compiled and executed, and you will speed up the code a lot. Unfortunately, this is not available in Python 3. It's only in Python 2, and then it was discontinued, unfortunately. So we are not gonna test it here. Okay, so we will first try numba, so because it's the easiest, and see how much does it help us. As I said before, numba is extremely easy to use. All we need to do is to add these two lines. Okay, of course, the first thing is you need to have numba installed, but this hopefully you already have because you've done the homework, isn't it? And now all you need to do is to import the numba. From numba, import JIT. JIT is a particular function, I think, inside this numba library. And then we're gonna use just this symbol. At JIT, non-Python is equal to true, which means that we want this code to be non-Python, or I think as far as I know, it's C at the end of the day. And this statement has to appear just before the function that you want to optimize. Okay, so this is optimization of a function. Now you have to be aware of certain things that are kind of non-compatible with numba. These limitations are similar also in F2Pi or Pi bint 11. So for me, they're not really very bad limitations. Namely, numba cannot accelerate the codes which use a Python list or dictionary, okay, or your own custom classes, okay. Now, why is that? Well, the way you can think of it is that if you have your built-in type, if you have your own type, which is not built-in type, then basically this numba would need to create a C++ type which is equivalent to your Python type. That's extremely hard. Unfortunately, it has not been done. So basically, as long as there is a simple connection between C++ type and Python type, then numba will likely succeed. Okay, so for example, floating point numbers in Python are definitely the same object as floating point numbers in C++. Integers, of course, they're translatable. Then strings are translatable. It turns out that arrays, NumPy arrays, which is very important, NumPy arrays are translatable from Python to C++. Okay, as long as the type is translatable, I think numba will probably succeed. But dictionary is much more complicated object that it does not have a good equivalent in C++. For example, there is something which is called map in standard applet library, but it's not one-to-one with a Python dictionary. It's slightly different. So therefore, dictionary and lists, for example, don't exist either in C++. List is also something more complicated because it can contain components or elements which are of different type. So in C++, you cannot have an array or a list which has different types. Okay, so therefore these types should be you should avoid these types if you want to use numba. Okay, but that's easy. I mean, you rewrite a function that works with floating point numbers typically, isn't it? And with NumPy arrays, and that's the type. That's the part that we're gonna speed up. Then you cannot allocate new arrays inside this accelerated code. So it's a good idea to allocate arrays before that, just before that, or after that. And you can't use recursion. That is usually not used so much anyway. Now it turns out that if you cannot get away with this restrictions, then it's a good idea to use Ceton instead of numba. But in terms of the speed, my experience is that Ceton and numba basically are almost equivalent. So if the numba works, if numba doesn't work well, then Ceton doesn't work well either. Except that Ceton allows you some to use, let's say, lists and dictionaries and so on. But in terms of speed, basically they're one-to-one. Now, however, Ceton is much harder to use. You need to know much more. While numba is just a line, basically, just adding a line in front. Okay, so therefore I decided that we're gonna present here numba. And the important point is this numba is something that is being actively developed and is getting better with the time. I would say every few weeks or every few months, you see that this numba is much better. When I was teaching this 2 years ago, I remember trying the numba and it didn't do anything. So it was completely useless. Some students were telling me, numba, let's try. I put this numba JIT in front, no change, okay? And I tried it this year, wow, big difference. So I hope that this is gonna continue to improve and it's gonna get even better in some years in future. Okay, so now we're gonna try this. Of course, we could just put JIT in front of our function here. So we could put JIT just in front of this function mand. Okay, so we could write here, JIT here, and that would speed up the code. However, the problem is that this wouldn't speed up the code so much. We can do much better. Why? Well, because we have 3 loops. I mean, we have this loop over ITR, and we have the loop over I, and we have the loop over J. Okay, and we can speed up all 3 loops at the same time with JIT. Okay, with numba. So why don't we do that? Why speed up only 1 loop? Because there is some overhead whenever you call numba. Okay, and you don't want to do it inside a double loop. Okay, you want to do it only once. Therefore, the idea is we are gonna rewrite the code just a little bit so that we can then apply numba in front of all 3 loops. So we're gonna write the loop over I, the loop over J, and the loop over iterations in 1 function. Okay, it's a small change. Okay, and now instead of, in order to break out here, we should not use return. Okay, so here we should not use return, nor before we use return, isn't it? Return here means jump out of the function. Okay, out of the function, and clearly we should not jump out of the function when we realize that that z becomes bigger than 2. What we should do is we should just jump out of this loop. Okay, and break is the command that jumps out of the innermost loop. Okay, that's something good idea to remember. Break basically sends you out of the innermost loop, so it brings you here. Okay, which means that then you go back to the top. Okay. So yeah, otherwise the code is the same. So basically z is equal to z squared plus z naught. Then we check every time it's absolute value of z is bigger than 2. If it is, then we save the result. But if and jump out. But if it's not bigger than 2, then we repeat. Okay. Yeah, so now that we have all this, and basically we allocate, oh, that's an interesting thing. Actually, I'm allocating the data inside this function, and it seems it still works pretty well. But I'm allocating I'm here allocating the data and set it to max steps. Okay, so I told you before that one way to allocate the data is to use here zeros, but another way is to use ones. Ones times max steps means that the entire data is set to a 2-dimensional array with components max steps in it. So basically this looks like 2-dimensional array. No, like a matrix, isn't it? And every component is equal to max steps. Okay, max steps, and so on. It's 2-dimensional array, isn't it? Because I'm multiplying max steps times ones. Yeah, why is this a good idea? Because, because max steps means that this is part of the Mandelbrot set, isn't that? So at the beginning, we set every pixel to like being part of the Mandelbrot set. But then here, if things are not in Mandelbrot set, we're going to change it here. We're going to change it in this step, in this place, isn't it? So I could use this. So here we're going to change it if it's not part of the Mandelbrot set, isn't it? But here at the beginning, we're going to set everything to be part of the Mandelbrot set. Okay. Yeah, and then how do we use this? Well, we just invoke this Mandelbrot Python with our minimum x, maximum x, minimum y, maximum y, and we time it, and then we use the im show to display. Okay, easy. Now, if we do that and don't use the numba, then it turns out that this is actually slower than original codes. The original code took 31 seconds. But if I use manpi numba, so this is this code, and I will comment out this JIT thing, okay? I'm commenting it out, okay? And I'm gonna execute it. And what you're gonna see here is that it's gonna take 90 seconds, but probably now that I use Zoom as well, it's gonna be even more than that. So the message is that putting these 3 loops together seems to slow down the code. I mean, to be honest, I don't know why it slowed down the code. Naively, I would say that the code should be equally fast or maybe slightly faster, because we are not calling the function all the time, but we have just one function. Right now seems almost the same speed. Yeah, well, that's interesting. When I don't use Zoom, it turns out that this code somehow it seems to be slightly slower. But the point is that it's the same. Because I used the wrong one. Mant numba. Okay, so Mant numba is, I think, if we don't use this acceleration, it should be slower than the original code, which to me it's counterintuitive, but I don't know exactly how the inner working of Python is and why this is slower.
Excuse me.
Yeah. Yep.
I'm not positive, but I can't make out your input line when you're in your terminal. It's like the line when you're actually inputting your commands. I can't actually see it. I think I'm like 2 or 3 commands behind.
Now do you see it?
Yes.
I see. So basically this share screen doesn't work all the way down to the bottom of the screen. I see.
Got it.
Now, do you see it now? Still okay?
Yes, I see your cursor. This is the first time I've been able to see your cursor.
I see. Okay. Thank you. Yeah. So I'm still waiting for this code to finish. It's clearly taking more than 31 seconds, isn't it? So the message is that the Python code itself got slower after we merged the 3 loops together. It's kind of counterintuitive. Supposed to be 90 seconds or something. Okay. Still not done. Well, maybe we can. When we wait for this, we can change the code back to manpi. Oops. Now it's done. Finally. Took forever. Yeah, 116 seconds. So this seems to be what, 3 times, maybe 4 times slower. So to me, it looks quite unusual. But now we're going to change this code with just adding this simple line. JIT non-Python is true in front of the function. Okay. And we also need to just from numba import JIT. This is the only 2 lines. Okay. And execute again. 2 seconds. Okay. So that's not a small thing. This is 50 times faster. Okay. 1 line 50 times faster. Now, even if you compare to original code, which needed 31 seconds, and now 2 seconds, is still a factor of 15. Okay. It's a huge thing. So we added 2 lines of code and we got factor of 15 speed up. That's amazing. Okay, so yeah, the important thing to demonstrate, what I want to say here is that these 2 lines from numba import JIT and JIT non-Python is true made the code faster for a factor of 15. Again, I cannot guarantee that this is always going to work so well. Sometimes does, sometimes doesn't. But nevertheless, it's easy to try. And if it helps, that's great. If it doesn't help, we can use something else. Okay, keep in mind. So this was the numba. Yeah, the next thing that I wanted to teach you is this dynamic update of the selected region. As we discussed last time, we can create. Now we're going to use numba again, and we're going to create this code that can. Yeah, so now I'm displaying here the Mandelbrot set, isn't it? And then I can select the region here, and I can display it basically by replotting it every time, isn't it? That's a nice feature. It's kind of animation. And I can do this again, and I'm displaying another pattern, a so-called self-similarity pattern, isn't it? So how do we do that? That's quite useful many times, kind of using this type of zooming in feature. So how do we do that? Well, Python has library that can help you that. It's actually quite easy. Now, how do we start? Here it is. What do we need? We need the following. We need to, yeah. So we already used a matplotlib before for basically imshow from matplotlib. So this command we already used, imshow. In this way that we display the data. Actually, before we were displaying 1 over the data, and somebody asked why 1 over the data. Well, because this is our choice. Now I'm plotting just the data. Okay. So the plot looked slightly different this time than before. Yeah, and here we are plotting in exactly the same way as before, imshow. However, the difference is that we are adding this imshow into something which is called axis, AX, okay, AX. So imshow is basically, the way you can think of it is a member function of class which is called axis, AX. And how do we get this class? Well, we do it by invoking this command subplot. Okay, so it turns out that inside matplotlib there is a command called subplot, and this subplot displays prepares a figure with several possible subplots. Okay, we are using here subplot 1,1, which means that there is only one plot in our figure. Okay, but you could use several. So you could use I don't know, 2 by 2, for example. Okay, so many times in scientific papers we need, I don't know, 4 subplots. Okay, and in this case we would say subplot 2 by 2. Okay, right now it's just 1, but we still need to invoke this because we're gonna be updating this plot. Okay, so this figure is going to be updated. Therefore, we need kind of access to this axis. Okay, so the first thing, instead of just using imshow, we're gonna need to invoke subplot that will give us handle on both figure and axis. Okay, so there are 2 things that the subplot returns. One is, you see, this is a tuple of 2 things, figure and axis. Okay. Right now, we are not going to do anything with figure, okay? Although there are routines with which you can change the figure, but we're going to deal with this axis because it turns out that this object axis is the thing that we need to tweak in order to modify when users change the X range or Y range. Okay, so how do we modify? Well, as I said, we're gonna throw on this axis our original plot. Okay, just like we did before. And then next thing, we're going to connect this axis with a routine which we're going to call AX update. Okay, and here we're going to also connect this axis with AX update, and the first connection is whenever X is changed, and the second connection is whenever y is changed. So it turns out we need to do the two separately somehow. So whenever the user changes the x limit, this routine is going to be changed, and whenever the user changes the y limit, this routine is going to be changed. Okay. Of course, we could just maybe use only one call here, but then the issue is that what if y axis is not changed? Then maybe this updates is not done. But this is a safe way. So whenever either x or y is changed, every time we call the function. Okay.
So, can we not do this without the subplot in this case, Professor?
Well, as far as I know, this callback thing needs to be connected with axis. So we need to get a handle on axis. And I think this is the easiest way to get a handle on axis. Because if you remove, let's say that you remove this ax here and just write callback, this doesn't exist. Okay, callback turns out to be a function for the class axis, ax, isn't it? So we need to get a handle on this. And you see, if we don't use this, we remove this. Okay, so then what happens is whenever you use imshow, we are actually throwing things on default axis. Default. Okay. Now, what is default axis? It's some axis that is always kind of whenever you invoke the module matplotlib, there is an axis that exists. Okay, but you don't have a handle on it. At least I don't know how to get a handle on it. It's hidden somewhere. Okay. So therefore, the best way to get a handle on your axis is by just invoking the subplot first. And now we are connecting. So what we did is we connected here the change of x and y axis with a function, okay, which is going to be called every time we change something. And this function here is ax update. So basically, this function here, function ax update, is actually this function, okay, that we are creating here. Okay, and we need to write the function, and this function has to have only one argument. And this argument is axis. Isn't it? Therefore, we need an axis. We need to throw it here, ax. And then inside subroutine here, inside this function, we can do anything with axis we want. Okay, there are several things that we can do with axis. For example, we can figure out what is the new x, what is the new y. We can figure out what we can apply new data on this axis. Okay. So let's first implement this and let's see what happens. So we could do the following. Yes, here I created a code. I can display it here. So in this code, we have exactly the same subroutine or function that we had before, which is optimized with numba. Okay, so that's what we used before. And now the only thing that I did here is I added this ax update, as I said before, ax update, ax set. Yeah, we need to add this line, ax set autoscale is on, autoscale on false. It turns out that if you don't do this, you have an infinite loop. Okay, so because this updating will keep updating somehow, and it will never break. So we need to do this. We're not going to go into details why, but for our purposes, we need to set this autoscale on is false. And then we can do anything we want here. For now, we're going to do nothing. We're going to just print that x or y was changed. Okay, we're going to print out we are now inside this routine. And then in here, we're going to, instead of doing imshow, we're going to do what I just explained here, get a handle on axis by using the subplot. Then we're going to display our data on this axis, and then we're going to connect when user changes x or y limits, we're going to connect this with this update. Okay, nothing else. Let me demonstrate. Okay, so first this up to now we are just here. We have this AXIM show. Okay, so the thing was displayed. We also connected. Of course, we also connected the change of the limits with this function, but this function has never been called because we didn't change the limits yet. Okay. However, if I click now here and change the limits, you see what happens. I got on my terminal, I got a message X or Y was changed, and I got twice this message. Why did I get it twice? Well, because I wrote here that either X is changed or Y is changed. In both cases, this needs to be called, and indeed this was explained to me now. Okay, and now if I do this, if I repeat this again, okay, again I get two messages: X was changed, Y was changed. But unfortunately, what has been displayed, of course, is some big pixel, isn't it? Because nothing has been done. I mean, I zoomed in, but the data wasn't changed on the display. Okay, so, and we go back, and now X or Y was again changed, but nothing has been done. So in next step, what we need to do is here, instead of just printing out that something was changed, we need to actually put some code in here, isn't it? Something that will actually change the display. Okay, so we can do something like first thing I would do the following. We can use Axis has something which is called view limit bounds. Okay, view limits dot bounds. This will give you the current minimum X, minimum X and minimum Y, and then the width in X and the width in Y, which we call X delta and Y delta. Okay, and of course with this we can figure out also what is the maximum X and maximum Y. Okay, and that's all we need. So now we can print. No, first we can write our X. X was always X start, minimum X, isn't it? This X start, then X end, then we need Y start and Y end. And then we can, for example, print X is equal to X. Okay, if we do that, and okay, I have syntax error. What did I do? X. Okay, now, oh my God, yeah, I'm very used to Python 2. In Python 3, you always need to have these brackets, otherwise it's an error. In Python 2, we didn't need that. Okay, once I've done that, you see that if I zoom in, okay, now I get a message that this range has been changed. First, it updated the X range, and then in the next call, it updated also the Y range. Isn't that? So both were changed, the X range, and then next one, Y range, exactly as we expected. Now, of course, we got a message that X and Y was changed, but we still didn't update the figure, isn't it? We still need to figure out how to update the figure. Okay, right now we just have all the data, but we didn't update yet. So what do we need to do next? Well, we need to call our numba here, and with the proper extension, with the new extension, isn't it? Now, in this case, we need to actually give an array rather than list. So we're going to call this numba array, numba with new extension, with the same max steps and the same nx and xy. And this will give us a new data. Okay, the data that we actually need to use. And this will still not do it. This will still not update the figure. We now just have the data for the new range, but we still need to update the figure. Isn't it? So how do we update the figure? Well, in order to update the figure, we need to add her several lines. I'm going to copy them. Okay, so what do we need to do? First, we need to take from the axis the last image. Okay, so this images here means all the images that were thrown into the axis. Okay, in this case it was only one anyway, but if there were more, you need to take the last one. Okay, this -1 means we take the last component from a list. Actually, this is a list. I think it's not an array; it's a list. So we take the last component from the list, and this we call IM. It's an image object, okay? But this is an image. Then this image, what you need to do is you need to call a function which is called setData, okay? And this function has an argument which is our new data, okay? Our new array. So this basically updates our imshow, okay? setData. And then we also need to add setExtend, which also corrects your x and y ticks and range. Okay, so we need to update the data, and we need to update the the axis, so that it's nice that it has correct range. And then finally, we need to do again something with the axis. We need to call figure canvas draw idle. Okay, redraw the figure really. This AX figure canvas draw idle is like show before. We had to call show when we are done with all the plotting. So here, instead of show, we need to call this redraw figure canvas redraw. Okay, but once we add these few lines here, and then we call manp dynamic py, we surprisingly see that that works. You see, now it was updated, properly updated. Okay. Again, seems to work quite well. And if I decide to go back home, it's updated again. Okay, so this is how it works. Yeah, so I think we finished this part, dynamically updating the region and exploring self-similarity. So for the homework, please implement this yourself. I mean, it's already on the GitHub. Okay, so what you actually need to do is either look into the code and familiarize yourself with the code, or if you are kind of already a pretty good Python coder, you might do it yourself and tweaking it a little bit, play with it, basically. Okay, so of course we didn't go through Python syntax yet, so I don't expect people who are not familiar with Python that they're gonna write their own code yet for this, but then you just play with it, doesn't it? Play with the code that I have done. So you can add some print statement in there, and like I did here during the class, print statement to familiarize yourself what happens. Okay, just get familiar, get some feeling of what happens in each step. Any question so far?
Yes, I have a question.
Yes.
So we define a function called x, like update, right?
Yes.
So when we call it, why don't we need like a bracket or like self.access update? Like we just write access update, but we don't have any input.
You mean in this line, why do we call it this way? Is this the question? Why do we call it this way in this particular place, or what?
Yes.
Okay, so because it turns out that this AX callback connect is itself a function that has as an argument another function. So this thing needs an argument which needs to be a function.
I see. I see. Okay, I see.
Itself is a function. It's not a call to a function. It's just a function. And then
I see.
function will be called later on when needed. Okay, but
Thank you.
yeah. So the important point is the argument. This argument here is the type of event, and this argument here is a new function that needs to be specified. And this function, you can call it any way you want. I call it AX update, but just needs to be a function, user-defined function, basically. Yeah. Any other?
Thank you.
Yeah. Any other question? Okay, so there is no question. Then we have a few more minutes, 6 more minutes. And what we want to discuss now is other ways of improving Python. So up to now we only covered numba, which is a very easy way of improving our code. But there are several other ways, as we mentioned before. In particular, F2Py, which connects the Fortran code, and PyBint11, which connect C++ code to Python. Now, the reason that F2Py is so popular is because it's already included in NumPy. So whenever you install NumPy, F2Py already exists. Okay, no extra installation needed. And the reason for this is because F2Py was used to create most of NumPy and SkyPy. I mean, these two libraries are mostly obtained by using this F2Py in this way. So therefore, why? Because most of routines, scientific routines, are actually written in Fortran, were written in Fortran and being used now. Now, PyBint11 is a different story. As you remember, we had to install it ourselves in our first homework, because by default, this is not what's being used. It turns out that, of course, combining C++ and Python is slightly more complicated, because C++ itself is a complicated language. It has its own type of classes, which are not exactly one-to-one with Python classes. And also the types that are being used in C++ are not exactly one-to-one with Python. So the compatibility between Python and C++ is not completely straightforward, okay? And therefore, it turns out that more sophisticated tools are needed to combine the two. But PyBint11 is a recent thing. The reason it's called PyBint11 is because it needs C++ 11 or higher. So they call it PyBint11 because C++ 11. It's not compatible with old C++ libraries. So C++ 11 or more, which is the standard that was specified in 2011. So it's 9 years ago. But you will notice that basically standard that was specified in 2011 was not properly implemented until just recently. Why? Because you know, when standard is being specified, then people who are working on compilers just start to update the compilers, and it takes several years before compilers actually support that standard. Okay, that's how this thing works. So C++ 11 is maybe available in most compilers for maybe 5 years now. It's still relatively new for compilers. Is a question?
Yes. F2Py is compatible with Python 3?
Yes. Well, that's a good question. It depends. It depends. On my computer, absolutely, because when I installed Anaconda, I used only Python 3. And when there is only Python 3 on your computer, then F2Py is actually F2Py for Python 3. However, if you have both Python 2 and Python 3 simultaneously on your computer, then F2Py you need to use F2Py 3 actually, F2Py 3. On my computer, F2Py and F2Py 3 are exactly the same thing, okay, because I have Python 3 only. But if you have both, then you will need to use F2Py 3. So the best way is just to experiment with them. if F2Pi works, then probably they're one and the same thing. Okay, so I was discussing PyBint 11, and the nice thing about this PyBint 11 is that actually it requires only header files, no libraries or compilation. Okay, why is this a good idea? Well, you know, whenever the code needs libraries, not just header files, but libraries, there is always a problem with compatibility between different compilers and systems. So, for example, I create some code, and I want to share with you. Okay, and you download this code. It turns out that if I produce some libraries on my computer, and I have some libraries on my computer, it will almost for sure not work on your computer because your computer is different. So library always needs to be compiled or produced, or needs to be compiled and set up for each computer differently, because there are different computers, they have different architecture. Okay, and that's always painful. Okay, so for example, BLAS and LAPACK needs to be compiled for your computer by your vendor, and you need to find correct distribution. You need to have some type of environment with which you download these libraries, proper libraries for proper operating system and so on. And that's always painful. However, when you need only header files are text files. Okay, text files that just have code, nothing else. And that's convenient. Why? Because I can be sure now that the header files that I have, I can easily distribute to anybody, to you, for example, or any other collaborator I have, and he can just use this header files in exactly the same way as I'm using them, and they should work. Okay, so that's the advantage of F2Pi. Therefore, I like it. Again, the point is no libraries, and no libraries means no code that is architecture specific. Okay, so on different architecture, you need on different architecture, you don't need anything that is architecture specific. So it's only text files. Yeah, so that's the reason that we're gonna use PyBint 11. Now the rest of the things that I here mentioned, Weave, Swig, PyCXX, and Ceton, these are other things that Weave we used in the past, but it's not anymore available in Python 3. Swig is something that several people use, but it's a little bit harder to master, and it's a huge thing. PyCXX is slightly smaller, but I think is older than PyBint 11 and somehow similar to PyBint 11. So I didn't bother to teach you that, although I used it in the past. And then there is Ceton, which again is somewhat similar to numba. So I'm not going to use both. I'm going to just use numba rather than Ceton. Yeah, these are all ways that one can speed up the code. Next time, we're going to discuss, we're going to go into details of F2Pi and PyBint 11. And numba was already covered. So, any question? Any question?
Are you sticking around for a couple minutes after class?
Yes, I am. Any other question? Okay, if there is no more question, then thank you very much. You can leave. If you have questions, you can stay, and we're gonna talk with. Well, we're gonna discuss the questions that anybody might have. Okay, see you on Monday.
Thank you. See you next Monday.
See you next Monday. Have a nice weekend.
I have a question.
Mm-hmm.
I even don't know how to turn on a Python coding like screen. Could you help me?
Just a second. I'm gonna stop sharing the screen, and
yeah,
you can start sharing the screen.
Ah, okay.
Can you start sharing the screen?
Yeah, let me try. I can. Yeah, I can.